We're going to start our exploration of adding and subtracting rational expressions with some simpler examples involving monomial denominators. Now, if you think of adding and subtracting rational expressions as just like adding and subtracting fractions, then it makes sense to actually start with some just numeric fractions. So if you have 2/3 plus 3/5, it's a fairly easy problem, but you need to create a common denominator, and how you do that is going to be much more important with rational expressions than with just ordinary fractions. So if you have a denominator of 3 and 5, you're looking for a common denominator. The common denominator is 15, and one way to generate two fractions that have that common denominator is just to take the first fraction and multiply it by 5 over 5, and the second fraction and multiply it by 3 over 3. The new fractions are both going to have a denominator of 15, so there's really no point in writing two separate fractions. We can just write this as one fraction with a denominator of 15 and then break the numerator into two parts. So the first numerator would be 5 times 2, which is 10, and the second would be 3 times 3, which is 9, and we end up with 19 over 15. And sometimes we'll be able to simplify at that point because there's a common factor in the numerator or the denominator. In this case, clearly there isn't, and so you're done. Now, if you notice, what we actually did in the first example was we multiplied the numerator and the denominator of 2/3 by 5, which is the denominator of the second fraction. And vice versa for the second fraction. We multiplied the numerator and the denominator by 3, which was the numerator of the first fraction. We could do the same for the second example and just multiply the first fraction by 9 over 9, second fraction by 6 over 6, and figure it out. And that's always going to work. The numbers are going to be a little bigger. So if you're doing this without a calculator, it's going to be a little bit harder, and you're almost invariably going to have to simplify at the end. You're going to have some common factors in the numerator and the denominator. But it is a viable technique that will always work. However, with rational expressions, you really want to avoid this, and you want to keep the denominator as low as possible. You want to find the lowest common denominator, and not just any common denominator. And so the way to do that is to do a little bit of work ahead of time, looking at the two denominators and identifying any common factors. So in this case, 6 and 9 have a common factor of 3. And the technique I'm going to use you probably wouldn't need to do with numbers, but it will be very important with rational expressions. So what you're going to do is rewrite the 6 as 3 times 2 because of that common factor 3 that we identified. And you're going to rewrite the second denominator as 3 times 3. So there's your common factor, 3. And at this point, the numerators haven't changed. The first one is 5, the second one is 7. Now, the way to approach this is you look at the first denominator and you ask yourself, well, what's it missing the second denominator has? They both have one factor of 3, but that second denominator has an additional factor of 3. And so that's what I need to add in, if you like. And I add it in by multiplying both the numerator and the denominator by 3. Effectively, I'm multiplying this first fraction by 1. I'm creating an equivalent fraction. It really hasn't changed value. We're just representing it a different way. Now I look at the second denominator and I make the same question. What is it missing that the first denominator has? Well, the first denominator has 2 3's, but it also has a 2, and that's what I'm missing, so I multiply this by 2 over 2. All right, now the two fractions have a common denominator, so I don't need to write two separate fractions. I can write this with one fraction. Now I can leave this as 3 times 3 times 2, or I can expand it. Once we deal with rational expressions, I would suggest not expanding it because it'll actually make it easier to simplify later. And really, once you've gone to the trouble of factoring these expressions, as we mentioned last time, you don't really need to expand them. So what are the numerators here? We have 3 times 5, which is 15, minus 7 times 2, which is 14. And so we end up with 1. And since we are writing this as a simple fraction, let's expand the numerator. 3 times 3 times 2 is 18. So we end up with 1/18. So this is essentially the technique we're going to follow for all these problems involving rational expressions. So let's take a look at a couple of examples. let's say we have 7 over 4x squared minus 2 over 3x. So it's a little easier with monomial denominators because we don't have to do any initial factoring. We just have to look at these and say, all right, what's the first denominator missing that the second one has? Well, it's missing a factor of 3. So we can multiply the first one by 3 over 3. And what's the second one missing that the first one has? Well, not only is it missing a factor of 4, but it's also missing an additional x. And now we've created a common denominator of 3 times 4 times x squared, in other words 12x squared. And so once again, once we've got the common denominator, no point in writing two separate fractions. We can just write this as 12x squared. And then we have 3 times 7, which is 21, minus 2 times 4x, which is 8x. We look for opportunities to simplify. There are none here. And so we're done, but remember, as always, with rational expressions, you should write restrictions. In this case, the restrictions are just x is not allowed to equal 0. All right, let's see a couple more examples. Let's say we have 2x plus 3 over 6x squared plus x minus 4 over 3x. Now, most of the time with monomials, you don't really have to do much work to identify the factors that are missing. You know, if it really helps you, you can rewrite or break apart the 6x squared into component factors, identifying the common factor, which is 3x. And so you have a 3x and then a 2x. And then it's pretty clear that you don't really need to do anything to the first fraction because it's not missing anything that the second denominator has. The second denominator, though, is clearly missing a factor of 2x. And so that's what we're going to multiply both the numerator and the denominator by. And so we end up with a single fraction. We can just write the denominator as 6x squared. We have the first numerator, 2x plus 3, that we didn't do anything to. And now we have to expand the binomial times 2x. So x times 2x is 2x squared. And then minus 8x. And we've got a little bit of simplification to do here. We should put the terms in declining order of degree as well. So we'll put the 2x squared term first. And then we have a 2x and a minus 8x. So those are like terms. We can combine them to get minus 6x. And then a plus 3. And this is all over 6x squared. Again, we look for opportunities to cancel common factors, numerator and denominator. There are no common factors to the numerator and the denominator. And so the only thing left to do is to write restrictions. In this case, x, once again, is not allowed to equal 0. All right, let's go on to a little more interesting example that involves 3 fractions. So what if we have x plus 5 over 3x squared minus x minus 2 over 2x plus 2x plus 1 over 6. All right, so we have to find a denominator that's common to all 3. And there are no common factors to all 3. The third denominator doesn't have any x's. And we can't identify any common factor to all 3. So the task simply becomes, what is the first one missing that the other 2 have? Now, the first denominator is really only missing a factor of 2. And you can see that the lowest common denominator is going to be 6x squared. The second one, therefore, is missing a factor of 3x. And the third one is missing a factor of x squared. So let's be careful about this. We're going to get one single fraction with a denominator of 6x squared. But we have a little bit of work to do. The 2 gets multiplied by the full binomial there, x plus 5, so we end up with 2x plus 10. Then we have minus 3x times x minus 2. Now here is one thing where you have to be very, very careful. It's very easy to get the signs wrong here. The minus 3x times x is pretty straightforward. It gives you minus 3x squared. Then you have a minus times a minus, so this should be plus 6x. And I'll show you or suggest one little thing you can do to check your work when you're once you're done, if you're ever worried about making an incorrect, writing down the sign incorrectly. And then finally we have plus 2x cubed, and then plus x squared. So we need to collect everything here and simplify. We'll start with the highest order term here, which is the 2x cubed. Then how many x squared terms do we have? We have minus 3x squared plus x squared, so that's minus 2x squared. Then we have a 2x and a 6x, so that's plus 8x. And then finally a plus 10. And this is all over 6x squared. Now you can see that every single coefficient is even, so we can take out a factor of 2. Cancel out the factor of 2 from both the numerator and the denominator, and we're left with x cubed minus x squared plus 4x plus 5 all over 3x squared. And again, the restriction x not allowed to equal 0. Now, the suggestion I had was, if you're ever in doubt, it is to select values of x. So if you pick a value of x, plug it into the original expression, and then plug it into your simplified expression, you can get a quick idea of whether you're on the right track or not. Now, it's certainly no guarantee that you've done it correctly. For instance, if you pick a value of 1 for x, you'll get a value in the original expression and a value of your simplified expression. If they're the same, it's a good sign. If they are not the same, that's a guarantee you've done something wrong. And so it's a quick way, if you've got a nagging suspicion that you've done something wrong, to really confirm that fact. Now, it really doesn't matter how many different values of x you plug in. You can't prove for certain that you've done it correctly, but if you plug in 1 or 2 different values and they are indeed the same, then chances are pretty good that you're on the right track.